Namaskar, I am Dayan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the examples on soluble groups. See here theorem example. Mm, A and B are soluble group if and only if A Cartesian product B is soluble. Solution now see here A only part. Let A and B be soluble group. So we have to prove that A cross A Cartesian product B is soluble. We know that the mapping F from A Cartesian product B from F from A Cartesian product B to A defined by F of AB is equal to A is an onto homomorphism. Therefore, by fundamental theorem of homomorphism, A Cartesian product B divided by kernel F is isomorphic to A, where kernel phi F is equal to singleton E1 Cartesian product B, where E1 denote the identity element in A. Thus, A Cartesian product B divides Cartesian singleton E1 Cartesian product B is isomorphic to A. As A is soluble, therefore A Cartesian product B divided by singleton E1 Cartesian product B is soluble. Further, the mapping G from singleton E1 Cartesian product B to B defined by G of E1 B is equal to B for each B belongs to B. Therefore, is isomorphism. Hence, singleton E1 Cartesian product B is isomorphic to B. As B is soluble by theorem, we get in a singleton E1 Cartesian product B is a soluble group. As both singleton E1 Cartesian product B and A Cartesian product B divide singleton E1 Cartesian product B are soluble group, then by theorem A Cartesian product B is soluble. If part now see here, suppose that A Cartesian product B is soluble as the mapping F from A Cartesian product B to A defined by F of AB is equal to A is onto homomorphism. We get A is a homomorphism image of a soluble group A Cartesian product B, and hence A is soluble. Similarly, we can prove that B is soluble. Now in next example, if H and K are normal soluble subgroup of group G, then show that HK is soluble. Proof now see here. So we know that HK is a subgroup of G. Therefore, by second isomorphism theorem, HK divided by K isomorphic to H divided by H intersection K. Now any quotient group of soluble group being soluble, we get H intersection H divided by H intersection N is the soluble. As since H is soluble, now isomorphic image of a soluble group is soluble, hence HK divided by K is soluble, then K and HK divided by K both are soluble will imply HK is soluble. Definition: a finite group, a finite sequence N0, N1, N2 dot 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 Nr of subgroups of group G is called a normal series of group G. If singleton E is equal to N0 is normal, N1 is normal, N2 is normal dot 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 is normal, N1 is equal to G, Nr is equal to G. The quotient group Nr divided by Nr minus 1 are called factors of the normal series, and so on. Theorem 1. A group G is soluble if and only if G has a normal series with abelian factors. Only part, let G be a soluble group. Hence, there exist positive integers such that g raised to k is equal to singleton E. Consider g raised to k minus 1. G raised to 1 G by theorem G raised to L. B is a normal subgroup of G for each I, and G raised to I plus 1 is normal in G array raised to I. Therefore, hence the sequence G raised to K minus 1 G raised to I G forms a normal series, and singleton is equal to G raised to K is normal in G raised to K minus 1 is normal normal in G raised to 1 is normal in G. Further, the factor G raised to K divided by G raised to I plus 1 are abelian groups for each I, 1 less equal I less equal K, and the G is solvable. G has a normal series. The singleton E is equal to G raised to K normal G raised to K minus 1 normal G raised to 1 normal G, and with abelian factors. If part, suppose G has a normal series n naught h naught s1 naught s1 hn with s naught is equal to singleton E and hn is equal to G, and with abelian factor. Thus singleton E is equal to h naught is normal, h1 is normal, hn is equal to G, and hi plus 1 divided by hi is an abelian group with 0 less equal I less equal n. Now we have to prove that hn divided by hn minus 1 is equal to G divided by hn minus 1 is abelian, that is G dash is subset of hn minus 1. Therefore G dash G double dash is subset of hn minus 1 dash. Hence, by transitivity, G n is subset of hn minus 2, and G2 is subset of hn minus 2. Continuing in this way, Gn subset of hn minus n is equal to h naught is equal to singleton E. Hence, G n is equal to singleton E, and this proves that G is solvable, and so on.